Let's begin. Today we'll wrap up the numerical description of data. It shouldn't take long. Where we left off last time, we talked about the 5 quartiles. Q0, which is the minimum data point in the data. Q1, where 25% of the data lie below that point, or the 25th percentile. Q2 is the 50th percentile. Q3 is the 75th. And Q4 is the 100th percentile. That's the maximum data point. So those 5 numbers together are called the 5-number summary, and they are very useful in summarizing a ton of data and reporting data. There's one more quantity that we can measure. It's a kind of range, but instead of taking Q0 and Q4 or the maximum range, if you take the difference between the 75th and the 25th percentile, so you're looking at the data right in the middle, from 25% to 75%, that's called the interquartile range, or IQR, and we will use that in a minute to be able to quantitatively identify outliers rather than just eyeballing an outlier when you plot a distribution, for example. So it's just a simple number, Q3 minus Q1, and you get your IQR. Okay, so what can we do with those 5 numbers? We can do a very nice looking plot called the box plot. You've probably seen those plots. It's usually like a little rectangle with a bar in the middle and 2 whiskers, one above it, one below it. And you're like, what the heck are they showing here? Is this uncertainty? Is this like error, etc.? It's none of those. It's just a simple summary of the data. It's in the slides. This IQR. Yeah, it should be. Scroll down on the slide. It's in the textbook too. So, okay. So here's what you could do with the box plot. The way we build the box plot, you take those 5-number summaries, which we did last time on this MPG data, the fuel consumption data. We had the minimum fuel consumption was 12.1 miles per gallon all the way to 35. So we got Q0, Q1, Q2, Q3, and Q4. If you draw your x-axis in the units of interest, in this case, we're looking at miles per gallon, and then you simply draw a little whisker or a little vertical line, or you could do this, you could flip this around and do these box plots vertically, it doesn't matter. But if you put in all of those 5 numbers to scale on this graph, so Q0 would be here, 12.1, then Q1 over there, Q2 over here. Remember, Q2 is the 50th percentile, so that's the median. Half the data are below, half are above it. Q3, and then finally you get Q4 or max, or your max. Then if you draw a little box over here, and you draw these 2 lines, that gives you the box plot. So whenever you see those box plots, you're not looking at uncertainty or error or margin, etc. The standard box plot describes the quartiles in a set of data. The first whisker, the lowest whisker, is going to be the minimum. The largest whisker is going to be the max, unless specified otherwise. We'll see an example in a second. So usually there's a key for this box plot, what it means. But the standard box plot always has the Q1 and Q3 right here in the box. And that's what? That's your interquartile range. So the width of that box is your IQR, the Q3 minus Q1, the interquartile range. And the line in the middle here is Q2. Now sometimes people will also put the mean value. This is the median, right? They would put the mean value as a dot. Could be here or could be there, which would indicate if you have an outlier or not. It's a really nice summary of a lot of data in just one simple box to describe how the data is distributed. Okay? All right. So, and then you know that between any 2 whiskers, you have 25% of the data in a standard box plot. Unless there's a key and they change this a little bit. Sometimes they put the minimum at 10% or 10th percentile, and this is the 90th percentile. That's okay. That's okay. Sometimes you see this put in at maybe 80th percentile, and you see a few dots after that. Those would be outliers. Okay? But in general, this is the standard box plot, and they almost always have a key with them to describe what's going on. Okay. So in what follows, I'm going to show you a bunch of data, box plots showing the distribution of average spring, so April and May, total phosphorus concentrations for the years 1979 to 2008 for 4 of the 5 large sub-basins that comprise the Mississippi River Basin. Okay, so what they've done, every year they've taken the average phosphorus concentration in spring. So they're probably measuring every day in April and May, and they average the whole thing. So you get 1 data point per year for each basin. Now going from 1979 to 2008, 39 years, right? That's a lot of, I can't even count. 30 years, almost 29 years. And so 29 years of average data, right? But that gives you another distribution, right? So you have a distribution of averages at each one of those basins, each one of those sub-basins. Okay. Now we're asked that we have some questions. So let's look at the bars first. So look at the upper Mississippi River. So here we flipped that box plot. Now, if there's a key or a legend for the box plot, then read that. In this case, the lowest whisker is in 10th percentile. That's allowed. Okay, they can do that. The 90th percentile is the top, but still the Q1 or the 25th is here. The median is the 50th percentile, that bar in the middle, not in the middle, inside that interquartile range, and the 75th percentile. Now, you know that inside the box there's 25% of the data, but here there's only 15% of the data, another 15% of the data. And they added the mean value as well as this black dot in the middle. They can do that, which is nice. Tells you if your mean is below the median or above the median, which would indicate a potential where the skewness is. Is it skewed to the left or skewed to the right? Okay, so now you look at these 4 box plots, summarizes data over 30 years, right, in one single summary for each one of those basins. So now we can do some comparisons. Let's see the questions. First question, what do the top and bottom bars represent in these plots? Well, according to the key, the top one is the 90th percentile. So that's the data point where 90% of the data lie below it, and 80% and 10% of the data are above it. And the bottom one is the 10th percentile. Good. Which sub-basin had the highest median spring phosphorus concentration? So median, we're looking at the bar inside the box, right? So that's going to be Q2. Which was the highest? It was the Missouri sub-basin, right? Because that bar was about 0.4, almost 0.4. It's higher than all the other ones. Okay. Now, what about this other one? Which sub-basin had the lowest mean spring total phosphorus concentration? So the lowest mean value. Lowest mean value should be this one, right? That's the lowest mean value. Okay. And then lowest value. Okay. And then which sub-basin had the largest interquartile range? So the largest width on that box is going to be the Missouri one, right? It's the largest interquartile, largest spread in the data. Okay. Now the IQR can also be used to identify outliers in the data. There's a few more slides that will be done with this. It's somewhat of an ad hoc definition. There's not, you could change those numbers, but this is kind of standard practice in statistics. And you look at your data if you suspect an outlier, because you might see a couple of data points far away on the right or on the left, and to identify if this is truly an outlier according to standard practice is you take your interquartile range, so that's the 50% of your data in the middle, and move up by 1.5 IQR. So you take Q3 and move up by 1.5 interquartile range, or start at Q1 and go down, go to the left by minus 1.5 IQR. If your data are outside that new range, so here you're defining a new range for your data, okay? If data falls outside of this range, then they are outliers. You can exclude them from the data if you want, or keep them, but then do your analysis, keep them just to plot them and identify that those are outliers, but then the rest of your analysis should be based on this new range, Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. Okay? Finally, one last definition we look at, and we're going to come back to many of these topics here once we do full probability and inferential statistics. But again, there are numerical summaries of data. And it's kind of, you have to learn statistical theory to understand why we use these numbers, but we can't do statistical theory unless we kind of build up our knowledge first. So we'll do this now, take it for granted. The z-scores or the standard score or standard scores are a very important measure in statistics, and it allows you to truly compare data without bias across different configurations. So I'll start with an example, and then we can define the z-score. So Jody apparently scored 87 on her calculus test. So she's taking section 1 with Professor A in her calculus, and was bragging to her best friend about how well she had done. I'm not sure she's her best friend now, but you know. Okay, so she said that her class had a mean of 80 with a standard deviation of 5. Okay, so 5 points. Therefore, she had done better than the class average. Okay, true, she's got 87. The class average was 80, and the standard deviation was 5, so she's still above 1 standard deviation. Now, her best friend, Ashley, to whom she was bragging, okay, was disappointed because she took calculus with Professor B, whose exams are much harder. Okay, and she had scored only 82 on her calculus test. So Jody had 87, Ashley had 82, so 87 to 82. Obviously, 87 is larger than 82 as far as I remember, right? So Jody did better. But Jody's class had a mean of 73, which probably indicates that if the students are all kind of on the same level, right, probably means the exam was harder for an average to be this low, 73. Okay? And her standard deviation in section B was, in section Professor B was 6. Did Ashley really do worse than Jody? I mean, numerically, 87 and 82, okay, Jody got 87, that's fine, you know, she got the higher grade. But Ashley's class had a much lower mean than Jody's class. So shouldn't we compare to the mean of the data where, you know, Ashley was operating, right? That would be a more fair comparison possibly. So this is what the z-score allows us to do. The standard score or the z-score allows us to compare data across different data sets with different means and standard deviations. That's the problem, is that the data, the distribution for Ashley's class is different than the distribution for Jody's class. To compare them, we need to normalize them to a same scale, to the same scale. So we need to bring those two data sets to a unified scale, so then we can do true comparisons. The z-score allows you to do that. It's a very simple definition. You take the numerical value that you're interested in, so the grade for Jody or Ashley, that will be x, and you subtract that from the mean value. So you're looking, how far away am I from the mean value? And then you divide, you normalize by the standard deviation. Okay? Now, this is a dimensionless quantity. It has no units, right? Because x and mu have the same dimension, and sigma has the same dimensions as x and mu. And when you divide them by each other, it gives you a dimensionless number. And dimensionless numbers are always absolutely comparable to each other because they have no dimension, they have no scale anymore. You've normalized everything to the same standard. So if we take Jody's class and do 87 minus her mean over her standard deviation, and then compare that with Ashley's class, 82 minus her mean over her standard deviation, then we have truly normalized both of those distributions to the same scale. We will learn later that what this does, it converts both of those distributions into a distribution with a mean value of 0. So then you can truly compare the two data together. Okay? So what happens in this case, so we have two formulas here because we have one for a sample and one for a population, but they're the same, so it doesn't matter which one you use. Okay. So then when you look at Jody's z-score, you get 1.4 dimensionless, and you look at Ashley's z-score, it's 1.5. So it turns out that Ashley did a little bit better than Jody because Ashley's performance compared to her classmates and her exam difficulty, right, did better than what Jody did compared to her class average and her exam difficulty. Okay? Now, if they had the same, now they probably didn't have the same exam. Okay, so if they had the same exam, you know, then I would say, well, you know what? Then that class did much better than, you know, Ashley's class because the average on Ashley's class was lower. But still, a z-score gives you one way to do these comparisons cleanly without just getting stuck in nominal values. It's just like cost of living, right? Oh, you know, your friend makes $150,000 in San Francisco, and you make $80,000 and you live in what, St. George, or no, some cheap place, you know, Harriman, let's say, right? They're like, who's making more? Yeah, you know, your friend is making more in San Francisco, but their cost of living is probably 10 times your cost of living, right? So when it's done, you need to normalize that to a common standard of living so that you can do a true comparison. Let's make a deal. I'm going to present you with this problem. We're going to come back to it in a minute, okay? So here's the situation. I have 3 doors, okay? I only know what's behind those doors. Number 1, 2, 3. Now, there's one car behind those doors, the car of your dreams, okay? Lamborghini or, you know, yeah, actually stick with that. It looks like a Prius or like a car from Domino's here, but that's the best picture I could find in the 5 minutes I had to prep this lecture for. And there's 2 goats. So door number 1 could have a goat, door number 2 could have a car, door number 3 could have a goat. You know, there's 2 doors have goats behind them, and 1 door has a car behind it, okay? So now I'm going to ask you, I'm going to see how good of a gambler you are, okay? You're going to pick a door, all right? You're going to pick a door. Let's say we pick door number 1. Okay, you come up, stand next to me, and say, okay, pick door number 1. Will you pick door number 1? Then there's 2 doors left. Then because I know what's behind those 2 doors, okay, let's say I'm going to go ahead and open door number 3. And there's a goat behind door number 3. Okay? Then I give you the option. Do you want to switch doors before we open? Okay, who would switch? Let's count. 1, excluding those who know the problem. 1, 2, 3. Okay, who wouldn't switch? Who? Then what's the other answer? Like half of the class didn't even. So, can you raise your hand again, those who would switch? Okay. Oh, you wouldn't switch? Okay. If you wouldn't switch, can you please lift your arm? I want to see the proportions. What are the others doing? I'm going to assume you're not going to switch. Or you don't know the answer. Oh, you know the answer. Oh, I didn't know. Oh, sorry. That's right. That's right. You know the answer. But because you didn't raise your hand when I asked if you know the problem. Okay. So many of you know the problem. Okay. So we'll keep it a secret, and we'll find the answer if you should switch or you should not switch in a little bit. Hopefully we do it today. Okay. We are going to start on a new topic now. So the first topic was descriptive statistics. We're done with that. Put that in the books. Use it to report data. Use means and averages and standard deviations and box plots and all of that to report your data, okay? We're done with that. Now we're headed towards inferential statistics, but to get there, we need to learn some probability. And, you know, who loves probability here? Oh, come on. Like, okay. Are you good at it? Pretty good. Man, I hated probability. I was like, it was the worst topic that I studied, and I did, if you look at, like, please don't find my transcripts, but if you look at my transcripts, like probability was like the word. Probably I had a pretty bad teacher, but you can blame things on others. But I've grown to appreciate the importance and power of probability and games of chance. Now, so don't beat yourself up as you're learning this. If you get frustrated and cannot figure it out, it's hard. It's hard because there's so many words, and words could mean different. Usually problem statements can be confusing, like Albert picked up 54 pieces of peaches, and Jennifer picked up, and you get like these questions. They can be annoying, etc. So don't beat yourself up. Take it easy, take your time. The good thing though is that once we get some of the basic probability principles, we're going to move on to distributions. Working with distributions is a little easier because you have well-defined mathematical formulas. And if you understand basic probability, you're not going to be computing chances and probabilities. You're going to be looking at distributions and getting probabilities from those distributions, which is easier when we're doing inferential statistics. But we have to go through probability fundamentals. It's only one chapter, and the best part of it is that you have to learn how to count to know how to do probabilities. So that's one of the aspects that is critical in probability and probability theory. These are not comprehensive learning objectives. Like I said, I'm building these slides as I go. But by chapter, at least you should be able to do the following: define all three types of probabilities, calculate classical and experimental probabilities, define and apply addition rules and multiplication rules for probabilities, and that will expose you to exclusive events, dependent and independent events, and what they mean. And we will do some limited set of like Venn and diagrams. Those could have pitfalls in them. Define and identify sample spaces, outcomes, and events so that we can use correct wording when we talk to each other about probability. Learn how to count in sample spaces. So, I have 2 dice and I'm throwing them. How many outcomes do I have? What is my sample space? Right? So be able to count all of those. Identify all the rules of probabilities and recognize how to apply them correctly, and a few more. All right, we'll start with the introduction, and we'll start with some definitions. A probability experiment or trial. So this is an experiment or trial. Remember when we said in statistics, when you do an experiment, go and start sampling people and asking questions, etc. This is connected to that. A probability experiment is any process with a result determined by chance. What is chance? Right? What is chance? Is it truly something inherent in nature, or is it the lack of our full understanding of everything that affects the outcome of a system? Okay, flipping a coin, is that a deterministic process? Well, if I knew everything about the coin, and if I knew the air resistance, and I knew the temperature, and I knew how fast I'm flipping the coin, and I can control all of that, 100,000 parameters, then possibly I could predict where the coin is going to land with extreme precision. But our lack of knowledge of all of those pieces of information, we call that chance. So that's one way I like to think of chance, is our inability to really know exactly everything that governs a system, that controls the outcomes of a system. It's a lack of knowledge problem. Well, at least that's how my chaos teacher explained it to me. And it's kind of makes you feel reassured about determinism in the world. So chance is outcome. Chance in systems is our lack of full knowledge of a system to be able to model it. So we're like, it's all chance. There's a chance of the coin landing heads or tail, right? Okay, so an experiment would be, for example, flipping a coin twice, or flipping a coin once, or flipping a coin and then taking a bite of a hot dog, and then flipping a coin, could be anything. That's an experiment. Okay? Each individual result that is possible for a probability experiment is an outcome of that experiment. So you can get head, tail, head, and tail in this experiment, right? So those are all outcomes. Each one of those is an outcome, or a combination of those are also outcomes. Those are the possible results that an experiment could produce. Okay? Now, the sample space is the set of all possible outcomes. Whether they occur or not, that's not your concern. But the set of all possible outcomes, so heads, 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 tail, tail, heads, tail, tail, in that sequence, right? So heads, tail, heads, that's an important distinction, right? So all of those 4 outcomes, they can constitute the sample space, okay? And finally, an event is a piece of that sample space. So, for example, and we call that a subset. So, for example, an event could be heads, then tail. So you could say, what is the probability when you're flipping the coin twice? That's your experiment. What's the probability of the following event that you get heads and then tail? Or it could be, what's the probability that you get heads and heads, right? So, or what is the probability that you get heads and heads then tail, or tail then tail, right? That is an event because it's a subset of all outcomes in the sample space. Okay, so outcomes are the content of the sample space. An event is one or more of those outcomes bundled together. Okay, you could have or, you could have and statements. We'll see as we evolve learning this. Okay, so now consider we're going to be primarily driven by example, and I think that's a great way to learn probability, and following pretty much what the textbook has laid out. We start with an example about an experiment in which a coin is tossed and then a 6-sided die is rolled. Okay, so you flip a coin and roll it. List all the outcomes in the sample space for this experiment. So we start with that question. So what do you think if we could get heads and 1, we could get heads and 2, heads and 3, heads and 4, heads and 5, heads and 6, or we could get tails and 1, tail and 2, tail 3, tails 4, tail 5, right? That's our entire sample space. Now you could write this any way you like. You could draw, you could draw coins with heads on them, and then the symbol of the die, or you could just simply list them any way you like. It doesn't matter as long as it's kind of clear to you, makes sense to you. And oftentimes with these limited outcomes in a sample space, when the sample space is small, when the outcomes of the experiment is a finite, small, manageable number, it's great to write it out, because then you can contemplate it and think about it cleanly. Once the number of outcomes explodes and becomes very large, then it's really hard to wrap your head around it. You have to do it kind of abstractly. But this is my sample space. These are all the possible outcomes. H means head, and then the number means what I'm getting when I roll the die. So I could get a head and 1, head 2, head 3, etc., etc. Now, then I have a second question. List the outcomes, okay, so the contents of the following event. The event says tossing a tail and then rolling an odd number in that sequence. So now that's a subset of the sample space, because I'm not interested in heads anymore, so I can exclude all of those. But then I need a tail and an odd number. So I have a T1, T3, and T5. Okay? So those are the outcomes in my event, or the content of my event. Later we will ask, what is the probability of getting T1 or T3 or T5? Right? We will ask those kinds of questions. Okay, we're just kind of defining things now. Here's another experiment that we will use in subsequent examples, so it's good to get it out of the way. Consider the experiment in which a red 6-sided die and a blue 6-sided die are rolled together. Okay, so you're in Vegas and you feel lucky, you start, going through the works and, rolling 6-sided die, 2 of them. Okay, if you've watched the Ocean series, Oceans 11, 12, 13, yeah, it's fun. Okay, okay, so now we want to list the entire sample space, list the outcomes in the sample space. So what do you think we do? What do you think we have? Red die is 1, red die is 1, and then blue is 1. Then red die is 1, blue is 2. 1, 3, and so on and so forth. But red 1 and blue 1 is not equal to blue 1 and red 1. Okay? Or, sorry, red 1 and blue 2 is not equal to red 2 and blue 1, for example. Although their total is the same, but the sequence is different. Okay? So this is what we would get, because we're rolling the red 1 first, so we're going to start with the red 1. So you get all the possible variations in the red, and then you fix, you get 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, and then 1, 2, 2, 2, etc., and so on. So red 1 and blue 2 is not equal to red 2 and blue 1. Okay? Although the total is the same, which I've listed here for a later example. We're going to use this sample space for later, but that's the true sample space of your experiment. Okay? That's the true sample space for your experiment. Okay. Next, list the outcomes in the event. So outcomes are the contents in that event subset that the sum of the numbers rolled on the 2 dice equals 6. Okay, so I'm going to take this and I'm going to look everywhere there's 6 here. So 5 red, 1 blue. Okay, there's 6 over here, and then 4 red and 2 blue. There's this guy, and then there's this guy, and then there's that guy, right? And then 1 red and 5 blue. Okay, so got 1, 2, 3, 4, 5. Okay, those are the outcomes in that event. Okay, so I have them listed over here. Okay, that's great. Now, be careful when asking this question that although you could have similar combinations, like 5 red and 1 blue gives you the same result as 1 red and 5 blue, but they are different outcomes. That's why I colored them red and blue. So be careful. You have to make sure, unless otherwise specified, that it doesn't matter, that you have to make sure to count all of those distinct outcomes, because the order matters. First one is red, next one is blue. Okay. Right. The sample space is the set of outcomes, not the number of outcomes. Well, yeah, you know that. Okay, here's another example. Also, this would be showing the different ways of how we could count things in an experiment, count outcomes in an experiment to derive the sample space. Okay, so you saw listing letters and numbers, or drawing the die, right? Or you could make a tree. Doesn't matter, whatever works for you, different ways to be able to count all the outcomes. And this is great for problems that have a small number of outcomes, okay? Consider a litter of 3 puppies that are known to be only solid brown or spotted at birth. Use a tree diagram to list the outcomes in the sample space for each puppy's coloring in regard to birth order, okay? So the tree begins with the 2 possibilities for the first puppy, solid brown or spotted, and then branches out for the other 2 birth in the litter as shown. So you could start, if you started with, so the first puppy, you got the spotted and then the brown, and then they could have a spotted and a brown, and then each one can branch out, and you can see how that number of things explode. And then you can, instead of doing the whole tree, you could have done just letters. Spotted, 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 so that would be this guy, and then spotted, spotted, brown, and then spotted, brown, spotted, and then spotted, brown, brown, and so on and so forth, okay? So just another way of how you could express the sample space. All right, so now we start to get into probabilities. Because once you know your sample space or your possible outcomes, you can figure out what's the likelihood of getting a subset of those outcomes, right? That's where we're headed to. If you know all your possible outcomes, okay, and you're looking only for a few outcomes, you can know the frequency of how often your outcomes or your event is going to occur. And hence we define probability. The first probability we'll talk about is subjective probability. We're not going to use that, but that's essentially making an educated guess based on your experience. Like, yeah, you know, I look at my kid scratches his arm or something. Yeah, I'm probably going to be fine. This is not going to cause an infection, right? I've seen it before, right? It's an educated guess, right? I cannot quantify. There's a 60% chance it's going to turn into an infection, right? Okay, experimental probability or empirical or observational probability, actually, you go in the field and run the test. You go and start flipping coins, rolling die, etc. And then you look for your outcome. How often is your outcome occurring? Okay, how often are you getting a total of 6 when you're rolling those 2 die? Okay, and you use that to measure, to estimate your likelihood. Okay, eventually this will be tied in with what we call the law of large numbers. When you're doing experimental probability, you need to do a large number of experiments to get an accurate probability. Now, how large? We'll understand that more as we go into statistics, but you need to do a lot, ideally infinite number of experiments. And as you get to that large number, you will actually recover what we call classical or theoretical probability. So classical probability or theoretical probability is the probability that you would count without doing any actual field work. You're just sitting on pen and paper. You look at your coin. You're like, okay, assuming this is an ideal coin, there's an equal chance of getting heads or tail. Or you have a die. There's a 1 out of 6 chance of getting any one of those numbers, right? That's your classical or theoretical probability. Okay? Under ideal, it's the most idealized situation, and most of the time we will be working with classical probability. Like I said, the difference between probability and statistics, in probability, you are using laws to make a prediction of what the likelihood of something happening. In statistics, it's the other way around. You collect the data and trying to infer what the law is, or if the coin is, for example, fair or not. All right, so now let's get into some numerical definitions and formulas. In experimental probability, if E is your event, so for example, getting heads in your experiment, okay? What's the chance of getting heads then heads if you flip a coin twice? So you go and flip a coin twice and you start counting. The first time you flipped it twice, you get heads, tail. Then you get tail, tail. Then you got tail, heads. Then you got heads, 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 heads. You do this 1,000 times. And let's say, you got 250 of those were actually heads, heads, or 240. Then you say, my probability of getting heads, heads is going to be 240 times that I get heads, heads, over 1,000 times running my experiment. It's just a frequency, okay? It's just how often did that event occur? And then you call that probability. Now, obviously, you'll be able to tell if you run this 10 times, it's not going to give you an accurate number because it's not enough chance, opportunity to get to the true value of that. So we write this as P of the event E. E could be anything. It doesn't have to be a math formula. It could be PHH, heads, heads, right? Or P obtaining heads and heads, or P of the likelihood of failing the exam, right? It could be a word, could be a sentence. But P of that event is equal to your frequency, how often you observe that event over the total number of outcomes in your experiment, the total number of times you ran your experiment, okay? Now, in classical probability, if all outcomes are likely to occur, so in other words, we're taking idealized situations. In other words, we take a fair coin. The likelihood of getting a tail is equal to the likelihood of getting a heads. Now, we can manipulate this if your coin is biased or your die is biased a little bit. We can adjust that. That's okay. We have tools to do that analytically. But in its basic definition, classical probability, if all outcomes are equally likely to occur, then the probability of your event E is the total number of your event E in your sample space, okay, the total number of times your event E occurs in the sample space over the total number of outcomes in your sample space. So S here is sample space. That's why we started defining sample space. It's important. You need to know what are the contents of your sample space and how many items are in it. Okay? So N of S gives me the total number of outcomes in the sample space. N of E gives me the total number of times this event occurred in my sample space. Okay? So that's the same thing as the experiment you ran. Except that in classical probability, you're not running the experiment 1,000 times or 1,000,000 times. You just look at your sample space, all possible outcomes for the flipping the coin twice, had only 4 possible outcomes, right? For the 2 dice, we had 36 outcomes. You don't have to run this 1,000 times. You just look, okay, how many times I'm getting this and that, divided by the total number of outcomes, and I'm done. I get my classical probability. Okay? All right, so let's try to work through this. First, we want to determine, we have a couple of questions first. So which probability is subjective, experimental, or classical? So the probability of selecting a letter at random from the English language is 1 over 26. Is that classical, experimental, or subjective? Classical. Classical, right? Because our sample space are the letters in the alphabet, 26 letters. Right? Picking a random letter, any letter, the chance is it's one letter out of all 26, right? And that's a classical probability because we know the sample space. We picked one event, picking a letter, we got 1 over 26. An economist predicts a 20% chance that technology stocks will decrease in value over the next year based on his knowledge of how other stocks have performed over the course of his career. Subjective, subjective, subjective. We're making an educated guess. Okay. A police officer wishes to know the probability that a driver chosen at random will be driving under the influence of alcohol on a Friday night. That's very specific. You know, Friday night, people are out. You know, work is done, school is done, and so they want to know what's the likelihood if they choose a person at random that they'll be under the influence. So in a roadblock, he records the number of drivers stopped and the number of drivers driving with a blood alcohol level over the legal limit. He determines that the probability is 3%. So it's what? It's pretty low. Is that what you said? It's way high. 3 out of 100 drivers. I guess that's pretty high, yeah. I don't know. So I thought it was pretty low. So is this subjective or classical, experimental? Experimental, correct. See, you guys are going to be great gamblers, so. Okay. All right, so let's run through some more examples. All right, Beck is allergic to peanuts. And at a large dinner party one evening, he notices that the cheesecake options on the dessert table contain the following flavors. So there's cheesecake, only cheesecake at the table. There's 10 slices of chocolate, 12 slices of caramel, 12 slices of chocolate peanut butter, and 8 slices of strawberry. Okay? Assume that the desserts are served to guests at random. So just randomly, they blindfold you. You go pick a cheesecake regardless of your allergy, regardless of whatever your preferences are. You're just going to pick a random cheesecake and be stuck with it. Okay? You're allowed to barter cheesecake with your neighbors at other tables, but that's beyond the point here. What is the probability that Beck's cheesecake contains peanuts? And then what's the probability that Beck's dessert does not contain chocolate? Okay, so we'll start with the first one. What is the probability that Beck's cheesecake contains peanuts? So in all of so we already have our sample space, right? What is it? It's all the slices of the cheesecake. There's 10 chocolates. So if I were to draw a diagram, I would put, 10 slices of C, chocolate, 10 slices, well, C is a bad, 10 slices of chocolate, 12 slices of caramel, 12 slices of chocolate peanut butter, and 8 slices of strawberry. That's your entire sample space. All of the cheesecakes and their flavors. Okay? So what's the total here? We got 10, 12, 12, 34, and then 8, 42. Okay? So we have 42 total slices of cheesecake. Okay? Now, what's the probability that Beck's cheesecake contains peanuts? There's only one type that contains peanuts. It's the 12 slices of chocolate peanut butter, right? So in that sample space, 12 of the outcomes contain peanuts. Classical probability says count those outcomes, 12, over the total outcomes, 42. That gives you the likelihood, the probability that Beck is going to get randomly assigned a peanut cheesecake that's probably going to cause him to end up in the hospital. Okay, so P of peanut cake, right? So that's my event. That's the best I could call it, getting a peanut cake, right? It's the number of outcomes in the event, which is 12 slices of peanut butter cheesecake, over the total outcomes in the sample space, which is 42 cheesecakes. So it's got a chance of about, 28%, 29% chance of getting really sick tonight. So probably shouldn't eat peanut butter, okay? Okay, so now another question. What is the probability? I know I should have a nice diagram to show you the comparisons, but next year, okay? You're the lucky ones that, is going to see a lot of text on my slides this year. Next year, I'll add some more graphics and be nicer, okay? What is the probability that Beck's dessert does not contain chocolate? Okay, so the sample space is still the same, and assuming he's the first one at the table, so there's 42 total slices, that's still our sample space. Now, what is the event? How can we pick that event that Beck's dessert does not contain chocolate? So 10 slices of chocolate, does that contain chocolate? Yes, it contains chocolate, so we can count that. 12 slices of caramel. Okay, so we got 12 that don't contain chocolate. 12 slices of chocolate peanut butter that contains chocolate. Then we have 8 slices of strawberry. So we have a total of 20 slices that don't contain chocolate. That is our event. It contains 12 slices of caramel and 8 slices of strawberry. Any one of those. It sounds delicious, right? Okay. So then what's the probability? Classical probability, the number of those outcomes in the event, 20. There's 20 slices out of the 42, right? So that gives you your probability then of getting something that is not chocolate. P of not chocolate. There's a 47% chance that he's going to, it's a pretty good chance, yeah, that he's going to get something that's not chocolate. Okay. All right. One more. This is interesting. So that's the problem with probability is like you can get entangled with the wording, and if it's not worded properly or clearly, if it's worded ambiguously, you can get in trouble. Consider a beginner. Do we have any archers in the classroom here? Wow. Okay. Pretty cool. I went arching for the first time in my life a couple of years ago. I was so sore when I went back home. You gotta hold that thing and pull it, and it's intense. That's pretty cool. Yeah. Did you do arching too?
Yeah, a long time ago.
Okay. Nice. Yeah, we went to this place in West Valley, the good archery club. Anyway, consider a beginning archer who only manages to hit the target 50% of the time. Okay, beginning archer. What is the probability that in 3 shots, the archer will hit the target all 3 times? Okay? All right. First thing you do is define your sample space. Your sample space contains all possible outcomes of what this archer will get after 3 shots. It could be target, target, target. It could be target, miss, target, or miss, target, target, etc., etc. All of those outcomes. You have to list them to count them. Okay. An easy way of doing this would be a tree. So on the first shot, he could get a target or he could miss. Then on the second shot, again, he could get either a target or miss. And then on the third shot, get a target or miss. So now you expand the tree, and then you get your sample space here. Hit, hit, hit. So hit, hit, hit. Hit, hit, miss. Hit, miss, hit. Hit, miss, miss, right? MHH. So miss, hit, hit, etc., etc. Okay, so that's your entire sample space. 1, 2, 3, 4, 5, 6, 7, 8. 8 outcomes. Later, we will learn to use combinatrix, and we'll be able to do these counts very quickly. Okay? But it's good to visualize them now, to think very simply about this. Now, of all, so we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes after 3 shots. Only one of them is hit, hit, hit. So classical probability tells you there's a 1 in 8 chance, or the probability is 1/8 for getting hit, hit, hit. Now you could read this as there's 1 in 8 chance. So in other words, if you go in practice, you're not going to hit them 1 in 8 times. You have to run the experiment for maybe 800 times, and then you'll be able to collect really your statistics. Okay, or 100 times, then you'll be able to see that you're really, so run it, throw the arch 80 times, and probably 10 out of those 80 times you're going to get, that's what this is telling you. You're going to get hit, target, target, target. Okay, you might get a little more, you might get a little less, but the more you play it, if you are consistently playing archery or darts, even darts, okay, so take a record of that. Okay. Now, okay, so this is interesting. Now consider the same archer again who hits the target 50% of the time. So still, at any time, he's holding the arch to throw the thing. Okay, the spear. What do you call it? The arrow. The arrow. It's like sometimes words like get out of my disk space up here. So. So at any time he's standing and throwing that arrow, there's a 50-50 chance. Because yes, you could argue that you hit them back to back, you have more accuracy, right? And the people who practice or target shoot, right? You can see that. But suppose that's not the case. Suppose he takes a minute, takes a break, rests his arms, and then tries again. There's always a 50-50 chance to get target or miss. In other words, the next trial, the next attempt is independent of the previous one or all the previous ones. Okay? That's the situation we're dealing with here. So, okay, so assume that 6 shots have been taken and each time the target was hit. So we got H, 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 H. What is the probability that the next shot will hit the target? 50%. Exactly. Right? Change nothing. The fact that he had a streak of hit, 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 hit doesn't affect the chance of the next trial. Okay? We're not asking the question, what's the likelihood of getting H, H, H or 7 H's back to back? That's different. If you're asking the question of getting 7 hits back to back, that's a very low percentage. But instead, what we're saying is, no, you're standing right now. Whatever you did in the past doesn't matter. What is the chance of hitting the target or not? Okay? And it is 1/2. Okay. I have another example. I'm going to skip it, but this is all to kind of show you. You can work through this example, please. Okay. All right. Okay, so this is what I wanted to lead to. That, okay, he hit it 6 times, and you'd think internally, oh man, I'm on a lucky streak, or like I hit them back to back, I'm going to stay accurate, I'm going to hit the target. In general, these events are independent of each other. And there's something called the false law of averages. So a family with 6 boys, what's the probability that the 7th child is a boy? It's still 50-50. Okay? Now, some I don't know, maybe there's some genetic predisposition to only carry one gender over the other, right? But in general, it's a 50-50 chance. So, there was a thing going like when everyone who rented when we were renting, when we moved to Salt Lake, every family they had a boy. So we had like this thing going on, like if you rent in this apartment building, you're only having boys. So anyway, but that's not true. Okay, there's 50-50 chance. Okay, do we need another break, or can we go on for another 15 minutes? 15 minutes? Okay. All right, the addition rules for probability. So right now we've only spoken about a single sequence of events. But sometimes we want to look at multiple outcomes in an event, right? So right now we've only had like one type of event that is kind of simple and easy to summarize. But sometimes we want to say, okay, what if you get 6 in your when you roll a die, or an even number, right? So how do you account for those kinds of probabilities? We introduce what's called the addition rules for probability. But first we formalize some definitions. For any event E, the probability of that event is always between 0 and 1. Because the event, by definition, is a subset of the sample space. When you divide the number of outcomes in the event over the number of outcomes in the sample space, that is always less than 1. If your event is equal to your sample space, then you're dividing 100 over 100%, you get 1. Okay? If your event contains nothing, then your probability is 0. And that's described here, that the probability of any event is between 0 and 1. The probability of the sample space occurring, it means any outcome occurring, is 100%. And then the probability of nothing happening is 0. Okay? The probability of getting is like feeling full from a hot dog if you're rolling a die has nothing to do with the die, right? You're just rolling the die, so it's 0. Okay. Now, some more definitions. The complement of an event, that will be super useful because as you will see later, counting is going to be hard with probabilities to count the sample space. Sometimes it's easy to count the complement or what's not your event because it's a smaller size event, and then you deduce the probability of your event. Okay? So we define the complement of an event E denoted by E complement or EC, E bar, or E prime, any one of those words. Okay? Don't be confused. You'll see all of those three nomenclatures, E complement or E bar or E prime. I might even write, P of peanut cake and put bar on top of it. That means probability of the complement of peanut cake, or everything that's not peanut cake. Okay? Is the set of all outcomes in the sample space that are not in E. So visually, if this blue box were your sample space, if your event E was here in orange, then the complement is everything that's not in E. Okay? That's not in E. Okay, so describe the complement of an event. Okay? Choose a vowel from the English alphabet. So who's like a grammar savvy and like word savvy here? So, okay. So what are the vowels? Okay. So we have five are, well, A, E, I, O, U. Okay, since five vowels are contained in the event, the other 21 letters or the consonants are the complement. So what's not in your event, right? You probably know this. Okay. Out of 31 students in your statistics class, 15 are out sick with the flu. I doubt that. I think they're like, just want to hang out home. But okay, so then the complement of 15 is the other 16 students, right? In your area, 91% of phone customers use phone south, then 9% do not use phone south. That's the complement, okay? You cannot say what they're using. We don't know that. Okay. Now, the sum of probabilities of an event E and its complement is equal to 1. As you can imagine from that sample space I drew, the sum of the probabilities of event E and its complement is equal to the sample space, so you get 1, exactly 1. Okay. We'll do an example, and then I'll give you the answer for that GOAT problem. If you are worried that there's a 35% chance that you will fail your upcoming test, means getting a failing grade on that test, what is the probability that you will pass the test? Okay? Pretty simple. The probability of passing is equal, the probability of passing plus the probability of succeeding is equal to 1. Okay? You can either pass or succeed. Right? And so the probability is equal to 1 minus the probability of failing, right? So that's how you would use the complement, and the chance of passing is 65% in this case, which is a pretty good chance. Okay? Another way we could use the, I promise you we're going to get to the making a deal problem next. Okay. Roll a pair of standard 6-sided dice. What is the probability that neither die is a 3? Oh gosh. Okay, so go back to the sample space we had listed before. All of those outcomes. Okay, you can pick all of the ones where neither die is a 3, or you could pick its complement, find that probability, and deduce the probability of your event. So if you list all of the die that have a 3 in them, that's going to be the complement of our event. And there's a smaller number in the complement. You could count all the ones that don't have a 3 in them, or count the ones that have a 3 in them. It's a smaller subset. It's easier to calculate. Those are all the possibilities of the complement of our event. So notice that each pair has a 3 in it, whether red, blue, or blue, red and blue, and red and blue. Doesn't matter whether the blue or red has a 3. It's still one of the outcomes. Okay. Then you could deduce that. Okay. So how many do we have? 1, 2, 3. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 outcomes. Our complement. Okay. In our complement. So we know that we have 11 over 36 in our probability of the complement. So the probability of our event is 1 minus that probability, which is about 70% chance. Okay? So that's how you would use the complement. You could count the event, but in this case, you got 25 items in the event, 11 items in the complement. Complement is easier. Okay. Now let's make a deal. Okay. So for those who chose, okay, so for those who know the answer, you should switch. Why should you switch? So the answer is that you should switch. Why should you switch?
Because like when you first choose the 33, like 3% chance of guessing right, but when you reveal that one of the doors is empty, then if you switch, you know, 50%.
Oh, but no. Don't switch. Okay, go ahead.
So you pick the first door, it's 33.3% chance.
Uh-huh.
Currently 66.6% chance that it's in the other 2 doors.
Uh-huh.
So when he opens one of the doors, you still have a 66% chance
Yes.
between those 2, but it's now
Yes.
reduced to 1.
Yeah.
And that door has a 66%.
Yes. So you're not wrong, but good explanation. So I want to explain it in terms of the sample space. Okay, so now I'm going to hide the goats and the car. We don't know what's going on. Okay. There's a 1/3 chance that the door contains, one of these doors contains a car. Okay, there's 3 doors, there's 1 car, 1 in 3 chances that the door you choose contains. You choose door number 1. Okay. So if you choose door number 1, probability that you get a car is 1/3, still 1/3. But the combined probability of those 2 other doors is 2/3. Agreed? Because there's 1/3 here, 1/3 here. Okay? Still, we haven't changed anything. However, when you open the door with the goat, you still have in this piece, you still have 2/3 probability, but instead of it being split between these 2 doors, all that probability went to this door now. Okay? All that probability went to that door. So yes, you should switch. Go on Google. I did this experiment yesterday. I spent like half an hour doing it. There's a simulator for this game. Now this problem is called the Monte Carlo problem. This is shown in the 70s. It's quite fun. I ended up watching it yesterday, like an hour of it, just kind of listening to it. The guy is like a gambler. So he brings in people to the show, and he's like, do you want to I give you $50, or you choose, what's behind this door over here, or what's behind that curtain. So it's like really intense, gets really intense. And this is like one of the climaxes of his show, in that you have these 3 doors, and he brings in the person, and they pick a door, then he reveals the goat, the other door, do you want to switch? And so what they did, at the time, this was pretty unique. So they sent this problem to, what's her name? Miss Savant, Marilyn Vos Savant. So she was a magazine columnist, but she had the highest IQ in history, 288. 288 among all women She had the highest IQ in history. So they sent her the problem, and she said, you need to switch. So then there were articles in the New York Times and Economist and whatever, and publishing in journals, people with PhDs in probability telling her she's wrong, until she actually showed them how to solve it. And it's exactly this. Now, with Bayesian statistics and with evolution of probability, we know the answer. We know how to explain it correctly. But it was a big fuss. It's called the Monty Hall problem. So go on Google and put Monty Hall simulator, okay? And on the way home, do one of them. Do just one of them. No switching versus switching. So run the experiment and don't switch every time. Pick a different door every time, but don't switch. And within about 150 experiments, I started getting to a 33% chance. Then I decided to switch. So I ran that about 100, 200 times. And then my probability of winning the car was actually 2/3, 2 out of 3 times. So it's incredibly amazing. Anyway, it's called the Monty Hall problem. This is one of the easiest ways to explain it, is like this diagram and thinking about your sample space. Okay? Pretty cool stuff. All right. Okay. Addition rule for probability. We'll do this and I'll let you go. Okay. Now, for 2 events, E and F, 2 different events, not the same, 2 different events, E and F, the probability that E or F occurs is given by the following formula. Probability of E or F is the sum of individual probabilities minus their intersection. So there's a diagram I can show you why do you need to subtract that intersection. Maybe we'll do that next time. But this is called the formula for probability additions. Every time you hear an or, what's the likelihood of getting 2 even numbers or 2 odd numbers, and you're rolling a die? You're adding probabilities. The word or means addition. Later we'll see the word and means multiplication. Okay? So this is the general rule for addition of probabilities. We will also define mutually exclusive events that have no outcomes in common whatsoever. Okay, so when 2 events have no outcomes in common, and this guy will be 0. Okay, I'll let you go. What the heck? Okay, I'm feeling lucky today, probabilistically lucky. All right, I'll see you on Tuesday. Godspeed.